Hello explorers and welcome to another video. Today we are doing the Advent of Code puzzle. The Git repository is linked in the description below, and if you want to see all of my trials and tribulations, you can see the full recording as a member of this channel. Day 9. Rope Bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine though. The bridge spans a gorge which is carved out of the massive river far below you. You step carefully as you do, the rope stretch and twist, and you decide to distract yourself by modeling rope physics. Maybe you can figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Due to nebulous reasons involving plank lengths, you should be able to model the position of the knots on a two-dimensional grid. Then by following a hypothetical series of motions, your puzzle input for the head, you can determine how the tail will move. Due to an aforementioned plank length, the rope must be quite short. In fact, the head and tail must always be touching, diagonally, adjacent, and even overlapping. Both count as touching. Okay. If the tail is ever two steps directly up, down, left, right from the tail must also move one step in the direction so it remains close enough. Okay. So we have there, so it moves around. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves one step diagonally to keep up. Okay. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and tail both start at the same position, overlapping. For example, R up, left, down, left, right. So this is a series of motions, moves the head right 4 steps and then up 4 steps, then left 3 steps, then down 1 step and so on. To update position of the tail, if the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. S marks the starting position as a reference point. So the initial state, the starting position, H and T covers S. Okay. After simulating the rope, you can count up all the positions the tail visited at least once in this diagram. S marks the starting position, which the tail also visited. And the hex marks the position the tail visited. So there are 13 positions the tail visited at least once. Simulate a complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? So we need to have a grid that has some kind of size, and then move the head and tail around on that grid and count all the places of the grid that it will encounter or will be. So this can be interesting. So first off we have that, which is our puzzle input. And if we look at day 9, we just have a bunch of these movements. So line, we split that by space, string move, and then we will do a move to move 0, move 1, and here we can do an integer parse int on move 1. So that's the move part that we want to do. And then we want to have, we can have public static int position x, and here we can say like 5 y5, like that, and then we can have public static short can have int there as well, grid new int, and here we can have a large value, so 100 times 100 perhaps. But let's start with something simple, so we just have 10 by 10 grid, or 20 by 20. So this we can actually plot, I believe. So let's start in the middle of that and then plot it out. So the move operation then, if we implement this, and then we should have pos of head and pos of tail. So move amount direction. So if we do a switch on direction, and then we have up, I think we will have a for loop from I0 to I amount, move a step in that direction. I think that is the easiest. So we do a switch on direction, and if up, do one thing, break, case, of course, case up, down, right, left, or left, right. We take the position of head, head Y, and do a minus on that, minus operation. And down we do a plus operation, and then we do plus X, we do a minus operation, and a plus operation. So now we just need to figure out how the tail should move. If pos head X let's see here, minus pose head tail x, and then we do math absolute of that. So if it's minus value, we will just have a positive value. So if this is smaller than 1 or larger than 1, then we need to do something. And if y is larger than 1, we need to do something as well. Just do a print out here and see what happens. Oh, not day 8, day 9. We want to try day 9. So let's stop that, close that, go up here, debug this one. So here we have a position of x that is 12. So then we need to move in that direction. So in this case, pose tail need to move towards pose x. So maybe we can do so if we do like that, then we would have 2. That minus 1 is the number we want to move against, right? So if we do the same for y, then what happens? I wonder if we just can say that tail x should be the same as position of head x. In those two cases. Yeah, it seems reasonable. So what we want to do now is actually remove these, and then we want to plot this out. So we want to take the grid, and we just want to keep tap on the tail position. So position of tail y times, and here we want to have also public static final int grid grid width of 20, grid height of 20. We can have grid size. We have the same width and height of the grid. It doesn't really matter. So here we want to tail y times grid size plus pose tail x. There we want to increase a value. And then here we want to do print grid. And just go through and do a simple print of this. For int y grid size y plus plus, and do the same for x. And here we want to do a system out print line, and in here we want to do just print. And here we want to take the grid y times grid size plus x. So that's what we want to print. So after we have printed the grid, we can have a printout here as well, just so we can see it in action. So let's look at the console. So we start there, and then we move up again. Oh, that was quite a jump. That's not right. Okay. So we want to continue to have this. -1. Okay, so this is just a movement, right? So either we should go positive or negative in that direction. So we pretty much just need to figure out if the direction equals up, then we want to do something else. And I realized that this is the wrong place because it's down here. So if it goes up, it should do a minus operation. And if it goes down, it should go a plus operation. If it goes left, it should do a minus operation and a plus operation. So hopefully that works better. So first we do what? Head X. Why does tail move twice? Yeah, that was wrong. Bug. So let's see. We are moving right. So the first, there we're on 13. So now we go up. How does this look? Yeah. So if we look at this graph, the last one here, it looks pretty similar to the 3-ish shape that they had. So let's look over at here. So they had 4 at the bottom, 1, 4, 2, 2. So I have the same shape as they have. So now I just need to go through and count the amount here. So if we skip this, print the grid, can be useful later on. So when we've done all the moves, we need to count the grid. So amounts so this will go through the grid, and we can do the same operation as we had with, no, we don't even need to do that. We just need to for I int I in grid, if I is larger than 0, then we add this amount, and then return amount. I'm not sure that we actually need a function for that. And then we take amount and print it out. So let's do that. We got 13, and in the example, 13 is the right amount of positions. So let's switch it up then and use our real data and see if we get the right solution. Out of bounds. The grid is much bigger. So let's do a grid that is 100 times 100, and we start at 50-50. Oh, yeah. We start at 50-50. Let's see if that works. It's still too small. So let's do a grid of 1,000 and start at 500. Did that work? So we have 5,902 positions. Let's see if that is correct. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So let's go over to part 2. A rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping towards you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid it being hit. Unfortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in the front, and it uses the same rolls as before. Using the same series of motions as the above example, but with the knots marked H1 to 9, the motion now occur as follows. Okay. Oh. Now you keep track of the positions that new tail visits. In this example, the tail never moves, so it only visits one position. However, be careful, more types of motions are possible than before. So you might want to visually compare your simulated rope to the one above. Here's a larger example, okay? So the actual end of the tail is what is interesting here. So we need a bunch more of these positions. So we go back to a grid size of 20 by 20 and 10 like that. And now we need 10 knots, so 9. Okay, so nine in total then. So let's do like that. So nine tail segments, like that. And at the start here, we want to arrays fill this position tail x or should we do like this and have the just rope x, rope y, and then we do rope x and fill that with the value 10, and rope y and fill that with the value 10. So then we will just take the rope x, y at 0th position and do that operation on it. Same goes for the next one. Rope x and yeah, so plus and minus, and then we need to end this operation as well, so like that. So these two absolute positionings, here we want to take the position of the rope x at the 9th position. That is what we want to plot here. And then we want to do a for loop from I equal to 1 and I less than the position of the rope, and then go through like that. So that's all the movements we want to do. And I think we need to do -1 as well. So here, should we go from, can do like this, so like that. So the rope position x at I, that's the head position, minus I plus 1, And in that case, we should do this to that one. And the tail y should be the head y. So now we have done exactly the same thing. The only thing is that we have more positions. So then we need to do the same for the y condition. So down here we will have the X rope instead. Now we are working in 4 dimensions. So here we're looking at Y. So like that. If we now run this. Oh yeah, we are not have not changed back to the simpler example. So here we got 5. That is incorrect. So how do we solve the diagonal case? So we do an else statement here. Another check here. So if both of those are true, so we can do like this. Boolean move X, and then we can have a move Y, just for readability. So here we have a move X and Y. And then down here we just have a move X and a move Y. So if we need to move both X and Y, so the first here is only applicable for I equal to 0. So if I equal to 0, then we do the first one here. Otherwise, we will just... so this is not applicable here. And here it's just I equal to 0. Then we do that specific move. Take into account which direction we want to move in. Otherwise, we just want to do the follow-up step down here. So we have already done the move up here, right? So I wonder if we can do this simpler. So here we have figured out that we need to move in either of those directions. Now we just need to figure out if it's positive or negative that we need to move in that direction. So I wonder if we can simplify this whole thing. So if we need to move in X position, then we need to figure out if position rope X at the where we want to go to is larger than where we are. Then we want to move one position in that direction, right? Else we want to move in the other direction. And same goes for Y, right? So we need to have and move XY. We need to use this Manhattan distance kind of thingy, I think. So if both of these values are larger than 2, then we need to move in the XY plane. And then we do both. Pretty much. So I wonder if this will be correct. We still have 1. But if we change the movement schedule up a bit. So they had an example that was a little bit more complicated here. For testing. So let's try that out. And then we can go up to our much larger play space with the grid size of 1,000. And if we run that, we have 22 steps. And they said here that it should be 36 places it visits. And I'm back, and it has been 12 hours since it's released, and I realized that I did a small bug this morning, but I was so tired, so I just totally missed it. So let's look here. This little thing here where I actually look at the last piece and then try to plot it out. I had a little mishap here. I should have had Y, of course. And if I run that, I will get the result of 36, which is the result that we expect, if I don't misremember. So let's go back here and check. Yeah, 36 positions. So let's do it with a large result set then and see if we actually end up with the right result. Like that. And then we need to have a very much larger field here. So let's go with 1,000 grid size, and then 500. Let's run that and see what we get. 2,445. So let's put that in. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So that was the solution this time. Oh my god. So little. I was so close to solving it this morning, but I was so tired. So I hope that you found this interesting. I hope that you learned something today. I learned that if you have a problem and you're stuck, then leave the problem for a while, go back, look at it again, and you will see what you have done wrong. So just leave and take some time off, think about the problem, and then come back to it, and you will have totally new eyes to look at the problem. If you have any suggestions or comments, leave them down in the comment section down below. Or if you have any code of your own for this problem, I would love to see your code solution. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.